In this lesson, we're going to be continuing our work in quadratics and looking at some of the algebraic operations, particularly multiplication. In order to do that, I'm going to be referring back to some work that I did in a previous lesson on algebra tiles. So if you're already familiar with how algebra tiles work, you might already know the answer to this one. And so I have an area here. And as you can see, this is made up of a number of tiles. So we've got an x squared, and we have 1, 2, 3, 4 x's, and we have 1, 2, 3, just the number 3. Now, that is what this area represents. So that's the area. The question then becomes, what are the side lengths? So the way you use algebra tiles for the sides is you just, a long side represents an x, and a short side represents the number 1. In this case, this represents positive x, this represents a positive 1, a positive 1, a positive 1. So all of those together represent positive 3. So this represents x plus 3 along this side. Down the other side, I have an x, and it's going to be plus 1. So my area is x squared plus 4x plus 3. My sides are x plus 3 and x plus 1. And the interesting thing, the reason why algebra tiles are useful to us is that x plus the sides, x plus 3 and x plus 1, if we multiply them together, well, multiplying length times width, that gives me an area. So these two things are equivalent to each other algebraically, and that's what we're going to be moving on to today. So here's another one. So what do we have in this case? We have a long side and another long side. Each of those long sides represents x, which means the overall side length here is 2x. And then we have negative 1, 2, 3, 4, 5. So this is 2x minus 5. And then we have another long side, which represents x, and we have positive 2 short sides, so that means plus 2. So in this case, we have 2x minus 5 is the length, x plus 2 is the width, and those two things together give me a total area of, I have 1x squared, 2x squareds, I have positive 4x's, I have negative 5x's, and I have negative 10. And then I would simplify that. 2x squared positive 4x minus 5x is just equal to negative x minus 10. And once again, if you have looked at, or if you're already familiar with algebra tiles, or you've looked at my tutorial, you might remember that I also mentioned that you could do this, which is you can take, for every pair of these positive and negatives, these cancel out. They add up to 0. So I can take out pairs of these, making zeros, until there are no pairs left. So all those in the corner there, those are all 0. And what do I have left here? X squared, 2x squared, a single negative x, minus 10. Now obviously in doing that, I've disrupted my whole rectangular shape. So I would recommend that you're actually better off leaving these things in place and from there just recognizing that you've got some positives, some negatives, and that you have to perform this addition or subtraction in your head. But if it helps you visually to eliminate them, you go ahead and do that. Now it can get a little awkward to work with algebra tiles, so I'm going to show you a way that you can do this on paper as well. Okay, so what we're going to be looking at today, the idea of multiplying polynomials. Polynomials means we have multiple terms, and expanding binomials, that's a specific type of polynomial, and that's the polynomial that has 2 terms in it. So that's what we were doing here. We were expanding a binomial times a binomial. So there's a couple of ways that we're going to talk about doing this on paper. I've already shown you, excuse me, I've already shown you how to do this using algebra tiles. So I'm also going to show you a graphical model that you can do on paper, or pure algebra that you can obviously do on paper as well. So just a review of some terms. These are things that you should have seen in your grade 9 course. A monomial, that's a single term. And I want to make sure that this is clear to you. This is a term. The 3 and the x are not terms separately. This is a number multiplied by a variable, and those together make up a term. 7, because there's no variable involved here, 7 is a term on its own. 5xy, even though we've got 3 individual items that are being multiplied together here, that is a single term, and so on. That's one term. A binomial, by definition, is made up of 2 terms. So here is our first term, here is our second term. Here is our first term, here is our second term. Here is our first term, here is our second term. And as you can see, they can be an expression with 2 terms, and those terms can be added or subtracted. So we have addition here, we have addition here, we have subtraction here. So some examples of terms: 2x is a term, 5 is a term, a is a term. (2b) is a term, m squared is a term, pq is a term. The negative stands for the subtraction. PQ itself is the term. And then we have a trinomial. That's an expression with 3 terms. So 1, 2, 3, 1, 2, 3. You can see this one is a quadratic expression, which is what we're studying in this unit. But a trinomial doesn't always have to be a quadratic. Here we have a trinomial that has a bunch of different variables, not just x and y. And then we go up into the generic form, which is, in general, these are all polynomials, an expression with any number of terms. They just get lumped together under polynomial. Okay, so returning to the algebra tiles just momentarily, we want to evaluate x minus 1 times x minus 2. So I'm not going to spend a lot of time talking about how to do this. This is covered in a previous lesson. But I want to form a length and a width. And it doesn't matter which way you form this. So I'm going to call x minus 1 down the side, and then x minus 2 along the top. And now that is my side lengths. So there's my expression, which I've changed into a visual model using algebra tiles. And now I'm going to figure out the area. So the way that works, I'd line up my sides. So x times x gives me x squared. Negative 1 times x gives me negative x. Negative 1 times x gives me negative x. X times negative 1 gives me negative x. Negative 1 times negative 1 gives me positive 1. Negative 1 times negative 1 gives me positive 1. You can see I have now formed an area, and that area is my answer. And so in this case, my area has an x squared in it. I don't have any opposite colors. That's a negative x, and a negative x. So that's just minus 3x. I don't have to cancel anything out. And then I have a plus 2. So here are my sides multiplied together. Here is my area. So how could I do the same thing using what we call an area model? What that means is that you actually are going to do the same thing we just did there, except for you're going to do it on paper. So I've got the way I normally recommend you do it is you're generally going to just want to create a box that's broken up into 4 pieces, into 4 separate pieces. And you don't have to worry about the size. This is one of the nice things about doing it this way. then you just fill in your sides. So I did it with an x here and a -1 here, an x here and a -2 here. And now, again, I form areas, except for now I'm going to do a little bit of the algebra rather than relying on the tiles. So what is x multiplied by x? If I had just this, x and x, well, that would give me an x squared. That's what I have here. If I had -2 and x, that's going to be -2 times that's -2x. That goes here. And so on. If I have x and -1, that's this x and this -1, well, that's -x, so that goes here. And finally, -2 by -1. -2 times -1, that's equal to positive, not +1. That's equal to +2, and that goes here. And that's it. That's the idea behind an area model. It just means you're using those small individual areas. You're finding the area, very simple arithmetic and algebra to get the overall. And then from there I go straight to my answer. That's got an x squared in it. -2x minus x is -3x plus 2. So the area model definitely works just as well as algebra tiles. It gives us the same result, but it can get you there a little quicker. So it's a step in the right direction. It can also make things easier when you have an awkward expression to do with algebra tiles. So here's 2x plus 7, 3x minus 5. So vertically, I'm just trying to save space, but actually it's going to be really difficult for me to do this. So if I use these algebra tiles as they are, well, there's my 2x, but now I have to somehow fit -7 in here. Okay, there's 3. That doesn't even fit. And now it's a little more awkward for me to do this, so I need 7, so I'm just going to have to bring these extra ones down and then fill them in here. Okay, so there's 2x minus 7, and then I go up to here and I need to do 3x. And, oh, sorry, that was supposed to be 2x plus 7, so I make a small mistake and I realize, well, I can use those up here. So you can see all the juggling. Now, obviously, me using this with technology, it has its advantages, but it also has its distinct disadvantages. So I don't need those. That was supposed to be 2x. This is 3x minus 5. I've got that right now. That's supposed to be 2x plus 7. So I need to bring down 7 of these. I need another 4 of them. And now I have to do my multiplication. And to do that, well, it starts off easy enough. I've got an x times an x, and then an x times an x, and an x times an x. Now I've got a -1 times an x. That's a -x. Bring all of these in. And then I've got another x times an x, so that comes down. And hopefully you're getting the idea here that even though I didn't increase these numbers by a huge amount, the amount of work that I have to do, the number of tiles involved, if you've got an actual set of tiles in front of you, usually they're limited. They try to give you an ample number of tiles, but it's not an infinite number. And so as I'm filling this in, this is really getting out of hand as far as the number of tiles that I need to use. So I think I've done enough here to illustrate my point. And I would need to continue to fill in. I need to put tiles here, and then I need a long tile, long tile, long tile, more small tiles in there, long, long, long. And you can see the number of tiles that I'm filling in here really gets out of hand. An area model uses a lot of the same thinking, but it really condenses things because once again, we're just using this generic 2x2 grid. So now I'm going to say 2x plus 7, 3x minus 5. 2x times 3x is 6x squared. When you multiply 2x times 3x. This is a review from grade 9. What you do is you multiply the constants together, so that's 2 times 3 gives you 6, and you multiply the variables together. X times x gives you x squared. Don't forget that this is x to the 1 and x to the 1. When you multiply these together, you add the exponents, so 1 plus 1 gives you 2. Negative 5 times 2x is negative 10x. Works the same way, except for this one doesn't have a variable. That doesn't mean 0. That just means you multiply the numbers together, but there's nothing else to multiply this by, so it just stays the same. 3x times positive 7 becomes positive 21x. I put that positive in there just to make sure it's really clear that it's offsetting against this negative. Negative 5 times positive 7 is negative 35. You can do this all in one step, or if you like, you could actually write it out in 2 steps, which is what I'm going to do now. Just to make sure it's really clear, all those different pieces. So I'm going to write out 6x squared, and I'm going to write out the contents of each box. So that's minus 10x plus 21x minus 35. And this idea that there are 2 of the x boxes. So we've got a single x squared box, we've got a single constant box, and then we've got 2 of these x boxes. Haha, that's a video game console joke. Minus 10x plus 21x is equal to positive 11x minus 35. These 2 x terms are going to combine into a single x term. And that's something we're going to see recurring later on. So just try to park that in the back of your mind and keep an eye out for it later. So that's the area model. Now, the distributive property. How do we do that? Well, the way the distributive property works is you take a term. Now again, remember, 2x on it is together a term. And 3x is a term, and 4 is a term, or negative 4, depending on how you look at it. So the way we use the distributive property is we take this value and multiply it by each of the values inside the brackets. That's what the distributive property is. And that's something that you should have seen both as review in grade 9 and earlier. So 2x multiplied by 3x is 6x squared. 2x multiplied by negative 4 is negative 8x, or minus 8x. That's the distributive property. Now, if I just had this 2x times this, then I would distribute that in, and I would get 2x times 5x is 10x squared. 2x times positive 2 is plus 4x. If, on the other hand, I just had positive 3 here, then I would distribute this in. I'd say 3 times 5x is 15x. 3 times positive 2 is plus 6. So actually what I'm going to do is I'm going to say that's what would happen if I had done my first distribution. That is what would happen if I did my second distribution. And if I'm doing both of them, there's a plus sign between them here, so there's a plus sign between them there. And so that becomes 10x squared plus 4x, positive, don't forget this is positive 1 times 15x, that's plus 15x, positive 1 times positive 6 is plus 6. And notice we've got those 2 x terms, we've got those 2 middle terms, and this becomes 10x squared plus 19x plus 6. Now, I don't want you going through this process where you are crossing out one term and then doing a distribution, that sort of thing. We want to get here in a more streamlined way, so I'm going to now show you what the distributive property is supposed to look like for a problem like this. And the way we're supposed to do it is we take the first term and we multiply it into each of the terms inside. And we take the second term and we multiply it into each. It's the same thing that we just did. I don't want you to write it the way I did before. I just did that to illustrate the idea. 2x times 5x is 10x squared. 2x times positive 2 is plus 4x. Positive 3 times 5x is plus 15x. Positive 3 times positive 2 is plus 6. I've got these middle terms which I combine, so that becomes 10x squared plus 4x plus 15x is plus 19x, which is what we had before, plus 6. So that's called the distributive property, and that can be applied to a monomial times a binomial times a binomial, which is really going to be our focus for this unit, a binomial times a trinomial, trinomial times trinomial, any combination. The distributive property is very consistent. The first term times each of the terms in the next bracket. The second term times each of the terms in the bracket. And you do that for as many terms as you have in the first bracket and for as many terms as you have in the second. Okay, we have a shortcut, or it's not really a shortcut, it's just an acronym to help us remember the distributive property specifically for binomial times binomial. So that really is the thing you do need to remember here. So this is binomial times binomial. That's what this is for, but essentially it is this. It is what we did up here, except for instead of the generic distributive property, now it's a very special form that we use for binomials. So this is actually one of our examples from before. We did this one using the area model. So the way FOIL works is we do first, so that's the first terms of each bracket. So first term times first term. And then we do outer, the outer terms of each bracket. So that's the first term of this one and the last term of this one, the ones that are as far apart from each other as possible. Then we do inner. So the inner ones are the ones that are as close to each other as possible. And then we do the last terms. So the last terms of each bracket. So yes, that's all very nice and colorful. And what does that give us? The first terms, 3x times 2x is 6x squared. The outer, 3x times positive 7 is plus 21x. The inner, negative 5 times positive 2x is negative 10x. And the last, negative 5 times positive 7 is negative 35. And then we combine those two middle terms, 6x squared plus 11x minus 35. And if you recall back to the area model, we had the exact same answer for that one. And you can use either of them, that's fine. Most of what you see as far as representations go will be this form. And that's it for multiplying polynomials, in particular multiplying binomials.